Hello, this is Mrs. Scarpel, and this is part 1 of Lesson 8 for Unit 2, the wow factor. In our last lesson, we began factoring, but when we were factoring, the a value of our trinomials was always 1. We call that the leading coefficient. In this lesson, we're going to be looking at factoring trinomial expressions when that a value is something other than 1. So we're going to continue to use those area model diagrams to factor. And the main question for this lesson is, how can we factor ax squared plus bx plus c when a is not equal to 1? So we still are working with Optima in her quilt shop, and sometimes she gives orders for blocks that are multiples of a given block. For instance, Optima got an order for a block that was exactly twice as big as the rectangular block that has one side 1 inch longer and the other side 3 inches longer than your basic X. So an open version of this is pictured here on our screen. And we see that we have 2x squareds, we see that we have 2 3x's, 2x's, and 2 3's. So we see double one block. So students in class were asked, what did you notice? What do you wonder? And one of the first things that was noticed was that there are 2 of the same block. Something else that was noticed, while we have our standard form, to the left of that equation, we see 2 times what we would find in one block. So the 2 that is factored out, we call that a common factor, is the number of identical blocks. I pointed out in class that the expression in the middle is what we call standard form, that ax squared plus bx plus c. The expression on the right, the far right, is factored form. And what makes that first expression special is that the common factor of 2, which we call the greatest common factor, is factored out. Now, when you factor out a common factor, it's like dividing, except it doesn't disappear like it would if we were completely dividing. So those were a couple of things that were noticed. Students didn't really mention anything about what they wondered yet at this point. So, using the idea of a common factor, when we worked through these 4 examples, we looked for, well, what's a common factor that I can take out of this expression or divide out of this expression to start with, so that we can end up with an expression that has the common factor followed by something in standard form. So if we look at 3x squared plus 21x plus 36, well, 3 is the greatest number that divides 3, but I also notice that 21 is divisible by 3 and so is 36. So it's like taking the distributive property and working backwards. What would I take times 3 to get 3x squared? Well, that would be x squared. What would I take times 3 to get 21x? That's going to be 7x. And what would I take times 3 to get 36? That's going to be positive 12. So if I check my work, if I were to distribute the 3, I should get the expression I started with. And then, knowing that that third expression listed on the previous screen was in factored form, I still need to factor my x squared plus 7x plus 12. So I'm just going to make a note. What I'm factoring is x squared plus 7x plus 12. And I'm going to create an area model for that. Now, in lesson 7, we knew that x squared would go in the top left corner, and the units, the 12, would go in the lower right. We also know that to multiply to get x squared, that's going to be x times x. But now we need to think of what multiplies to give us 12. Well, that's 1 times 12, 2 times 6, 3 times 4. And of these factor pairs, which ones can I use so that when I have these boxes that I fill in, will combine to give me 7x? Students pointed out, well, that's going to be 3 and 4. If we have 3x and we have 4x, and we add them together, we're going to get 7x. So that gives us an x plus 3 on one side, and that gives us an x plus 4 on the other side. So the fully factored form is going to be 3 times x plus 4 times x plus 3. And that's our fully factored form. So if we take a look at example B, again, what's the greatest common factor that I can factor out of these 3 terms? It's going to be 2. All of them are divisible by 2. So 2x squared divided by 2 leaves me just x squared. 2x divided by 2 leaves me 1x. Negative 4 divided by 2 leaves me negative 2. And then again, let's look at how does x squared plus 1x minus 2 factor. So we can create an area model. We have our x squared in the upper left. We have our minus 2 in the lower right. It has to be x times x to get x squared, and the only factor pair of 2 is 1 and 2. So if I have 1 times x is 1x, and 2 times x is 2x. In order to get this positive 1 that I have in the middle, I'm going to have to subtract 1 from a positive 2. So that means I'm going to have an x, or one factor of x plus 2, and the other factor will be x minus 1. And just to double check, negative 1 times positive 2 will multiply to give me this negative 4, or negative 2, excuse me. So the fully factored form is 2 times x plus 2 times x minus 1. Example C, again, looking for a common factor. In this case, it's 3. So we have x squared minus 9. Now, this is different in that we have a binomial. It only has 2 terms instead of a trinomial like our previous examples. But we can still use an area model. We just have to think a little bit about, well, what's going to happen to that middle term? So we have the x squared, we have the minus 9. That's x times x for x squared. But we need these two boxes to cancel each other out because we don't want to be left with an x term. Students pointed out, well, if we have a positive 3 and a negative 3, that would give us a positive 3x and a minus 3x, and those combine to equal 0. And negative 3 times positive 3 multiplies to give us negative 9. So we have 3 times x plus 3 times x minus 3 as our final answer. D, starting out the same way, what's the greatest common factor? And students only identified 5 to begin with, but I'm going to show you something here in a little bit. So if we factor out a 5, we have x squared plus 2x left behind. Now this time we don't have a c value. If you don't see a c value, that means its value is 0. So if you want to use an area model, that units is going to be 0. And we can have the x squared, and we know that's going to be x times x. Well, in order to multiply and get 0, one of the factors has to be 0. So I'm going to place a 0 on this side, and 0 times x is going to be 0x. But I need these two to combine to give me 2x. Well, that means I'm going to have a 2x. And what would I take times x to get 2x? That's going to be a positive 2. Now, if you think about it, x plus 0 is the same as just saying x. So one of our factors is x. The other factor is x plus 2. Now when I write this in factored form, I'm going to go ahead and just write 5x, because that means 5 times x. And then my remaining factor is x plus 2. We could have identified the 5x as a greatest common factor to start with, because both of our terms have an x in them, and we could have factored out or divided out a single x along with our 5 to do the factoring. So one of the things, or the first thing you're going to want to look at with any factoring in this lesson is there a common factor that we could factor out first and then do any remaining factoring? Now back to Optima. She's offering her customers lots of options, and one option is to have rectangles that have side lengths that are more than 1x. So in this open version, this side has a length of 2x, while the other side is only x. There's an additional inch and an additional 3 inches. So what do you notice about the diagram and the equation for area? What do you wonder? Well, one of the things students noticed, we only have 2 expressions here. We don't have one with a greatest common factor. So we said there aren't any common factors. Students pointed out that we have a 2x squared instead of x squared. So it's no longer x times x, but x times 2x. And it was also pointed out that 1 times 6, or 1 and 6, if we're just looking at these two values here, these coefficients, that 1 and 6 are not multiples of 3. But we haven't, in class anyway, talked about if 1 and 6 are factors, I shouldn't say multiples, are not factors of 3. But we haven't just talked about if they're factors of something else, which we will cover in part 2. So we were given the standard form 5x squared plus 8x plus 3 and a partially completed diagram. And the task is to take some of the things we noticed before and fill in this diagram to find the factored form. If we look at the values of 5, 8, and 3, there is not a common factor of those 3, so that's why we have to go ahead and put 5x squared in this upper left corner. Your units will always be in the lower right. Now, because 5 is a prime number, I know that 5 times 1 is the only way I can multiply and get 5. So we're going to have 5x times 1x gives us 5x squared. I also know that 3 is a prime number, and its only factors are 1 and 3. So I'm going to place the 3 on the same side as the 1x and the 1 on the same side as the 5x, and just see what happens with my model. So 1 times the 1x is 1x. 3 times the 5x is 15x. But remember, we want 8x. Is there any way I can combine 15x with 1x and get 8x? I hope you're saying no, because 15 plus 1 would be 16 and 15 minus 1 would be 14. So let's take the time and just switch where the 1 and 3 are placed and see if that makes a difference. So let's look at 5x plus 3 and 1x plus 1. So the 1 times 3 is still going to give me this 3, but I have these rectangles I need to think of. So 3 times 1x is 3x, and 1 times 5x is 5x. And if these values are both positive, they will combine to give me 8x. And we have in our factors that they are both positive as well, so positive times positive will give me that positive 3. So our factored form is 5x plus 3 times x plus 1. You could write 1x plus 1. That's perfectly fine. It's just not common to see it that way. So we're only going to take a look at examples 5 and 6. That's as far as we got in class. And we're going to complete our factoring. So again, we have a partially completed diagram for us for number 5. We have 2x squared in the top left. We have 3 in the lower right. If we think about 2x squared, that's going to have to be a 2x and a 1x, because 2 is a prime number, and we already know that 3 is a prime number as well. So I'm going to try 2x plus 3 and 1x plus 1 and see what happens. Keep in mind, we're looking for a 7x when we finish these. So 3 times 1x is 3x, and 1 times 2x is 2x. Well, the most these two can combine and give me is 5x. That's not 7. So let's switch the two numbers around. So we have x plus 3 and 2x plus 1. So 1 times 1x is 1x. 3 times 2x is 6x, and if I add these two values together, I will get 7x, and I still have 1 times 3 gives me 3. So the factored form for this one is x plus 3 times 2x plus 1. So for number 6, we're going to draw our own area model. If we look, there isn't a common factor of 2, 13, and 15. 13, in fact, is a prime number. So we're going to have 2x squared in the top left. We're going to need to have plus 15 in the lower right. We already know that to get 2x squared, we need 1x and 2x. 15, though, could be 1 times 15, and it could be 3 times 5. Now in class, students were quick to say, oh, 1 and 15. If I take 15 times the 1x, I have 15x. And if I take 1 times 2, I have 2x. And if I subtract 15 with a positive 2x, I will get negative 13, which is correct. But don't forget about this sign on our units. That sign is a positive. And if I take a negative 15 times a positive 1, will I get a positive 15? No, I won't. I'll get a negative 15. So it's not going to be 15 and 1. I'm not even going to switch them around because 2 times 15 is 30, and that's just going to take us too far away from negative 13. So let's try 3 and 5. If I take 5 times 2, I'll have 10x. If I take 3 times 1, I'll have 3x. If these are both negative, I would combine to get a negative 13x, which is what I want. And if the 3 and the 5 are both negative, when I multiply them, I will get a positive 15. So the factored form for this trinomial is x minus 5 times 2x minus 3. Now if you had been doing this on your own and you had placed the 3 and the 5 in different spots, do you think it would have mattered? Well, 2 times 3 would be 6, 1 times 5 would be 11. We wouldn't have gotten the 13. So you do want to definitely check that everything inside this model will combine or simplify to give you that original trinomial expression. And we will pick up with example 7 in the next video.